Thank you very much, Erica. Good morning, good afternoon, everybody. Thank you for joining us today. So, Erica says, my name is Chris Woodend, and just so you can have a visual of what I look like, unfortunately, there I am, my lovely mug and a bit of my bio. As Erica says, I'm the subject matter expert at API for optics. I've been with the company for the last 8 years, but I've spent the last 28 years working in microelectronics and optoelectronics. I've held roles from engineering all the way up to technology development manager, and now I'm helping the company do more of a technical role, getting out to the customer and explaining what we are, what we do, and how we can help you. So we move on to the next slide. Today's topic is obviously, why copper can't create anymore? For many years, copper has been used to transmit power and data due to the fact of being one of the lowest loss transmission medias and been able to transmit over long distances reliably. But as technology has advanced, optics is now starting to edge out copper, and the limitations of copper are starting to appear in the industry. Most of this is being driven by the fact that the data rates are increasing and signal integrity is required. Some of the new intra-satellite systems require 1 terabyte of data being transmitted every second. There's also the distance increase. So before you need an amplifier or a boost signal, customers now want the signal to go further before they need to add that electronics. Obviously, as we've seen through the years, security of data is becoming far more important. And obviously, there's an advantage as we go forward with optics. And one of the key ones is the reduction in overall project costs for programs. Everything's getting more expensive. We need to try and drive costs down. This first graphic illustrating the fact that as data increases and distance increases, copper starts to struggle with its transmission. And this one is purely about distance and nothing about attenuation by distance. So as you can clearly see from this, as you start heading up into 1 gigabits and 10 gigabits range, and you want to be sending information over 100 meters, multimode fiber kicks in, so you're going to need your fiber optics in there because the copper is going to struggle. And as you go higher in your data rate and higher in your distances, you will end up in single mode fiber. But currently, we'll only be discussing multimode, as most of the distances in the industry currently are sub 500 meters. So the links suit multimode fiber completely. The next issue we hit with distance is then attenuation or signal integrity. So where we have on the graphics here is on the left-hand side, we have what copper can do. And this dB loss is, for the first two, for the backplane and the improved backplane materials, is only over a distance of 0.8 of a meter, and you will end up with 20 dB signal loss. Once you get to the coaxial low loss, so essentially similar to fiber long distance, the losses aren't as great. But as you can see, for over 20 meters on a 40 gigabit signal, you will lose 20 dB of signal. And that's quite a huge loss. As you can see, if we go to the right-hand side for the optical fiber, that anywhere between 1 to 100 gigabits of data, you will see nothing more than a 3 dB loss, and that is over 1 kilometer distances. So as you can see, there's a significant improvement in signal integrity and signal distance as you move to optics as an advantage over our copper systems. Depending on your application, you can see that if you're just on a board, it's not too bad. As soon as you're off the board and you start to expand along a distance of an aircraft or a vehicle of any description, you will start to incur greater loss if you stick with copper. you move within the optics, you can see that you can go a fair distance without major signal loss, and before you actually have to put any boost systems in there.
Hey, Chris, we have a question from the audience.
Okay.
Why is APITech focusing on the multi-mode instead of the single mode?
So API have concentrated on multi-mode for two reasons. One, a voice of customer. So for the majority of military applications we've discussed, military already have multi-mode in the system. So therefore we need to fit into that. So we're not driving any rewiring, recabling costs. We're fitting into what the customer requires. And as I said earlier, very similar, another reason is distance. Most of the avionics systems do not require links of in excess of 500 meters. And multi-mode systems are perfectly good for that distance with minimal loss. You only really want to start moving to single mode if you're talking 10 to 20 kilometers of length of signal. Also, the fact that single mode is another step up. It's a more expensive product than a multi-mode, and its primary use is long distance. So if you're used to people making telephone calls and using voice over IP, that's more of a single mode. It's more of a telecoms application where you want to send things long distance without having to put any boost in there. I hope that covers the question.
Understood. Thank you.
Thank you very much. So this next slide, and I know it probably sounds a little bit like I'm beating copper up. It's done us proud for many, many years, but obviously as technologies advance, we need to move with that. This particular graphic shows as copper's gone faster, we go 5E, we go 6, Cat 6, Cat 6A, Cat 7. That's to increase to go with the gigabit Ethernet and 10 gigabit Ethernet, and then topping at 40 gig Ethernet. So you can see from this table, it shows not only have you got a size diameter problem with copper, and also a bit of a bend radius issue with copper, you also get only 4 twisted pairs. So you can only actually send 2 transmits and 2 receives, or a combination down one particular cable that's of between 5 and 8 millimeters in diameter. If you move to the copper and you look at the OM2, OM3, OM4, and the OM numbers are just iteration. So OM2 was the first fiber that came out for the highest speeds of the 10 gigabit and the 40 gigabit. And as you can see, the distances are impaired. OM3 and OM4 are an optimized fiber that's designed for 10 gigabit and up to 100 gigabit operational. They come in either a single or 12 fibers. So of course with fiber, you don't need a matched pair. So for every fiber, you're getting either 1 transmit or 1 return signal. So you can buy this in either a 1 to 12 strands in a fiber, in a cable, and that cable is only 3 millimeters in diameter. You can see it has an extremely good tension pull. So we're talking 1,000 newtons can be applied to this glass fiber, where people used to be very concerned it would fracture. You can put in excess of 1,000 newtons on there. And also this table clearly shows you are looking at huge distance improvement. So if you took the best 10 gigabit copper Ethernet, you go 100 meters. If you take the best 10 gigabit in the optics, you're up at 450 meters of transmission with no signal loss. So again, it's a great advantage over the distances, over the size and volume that you need to take up by putting the optical cable through compared to the copper systems. So the next slide again, is starting to say where copper will no longer will be able no longer to support. We know from studies done that copper is now can be pushed to about 18 to 21 gigabits per second, but of course you then have your huge attenuation loss. So we started to run out of the bandwidth at that point. So we have lots of applications now in industry that are pushing us way beyond that. So for example, here we see applications that are 100 gigabits per second per meter. And as I suggested earlier, some of the space applications we see now are 1 terabit per second per meter. So without the optics in place, you would not be able to do a 10 gig system between racks, so in excess of 100 meters. And as you start to go to your 100 gigabits and you're up to 3 terabits, you're talking 1 meters within your backplane. So again, your optics gives you a great advantage over these distances with these transmission data rates, but also the fact that the copper will not support these now. It's proven fact from lots of studies that copper is now topped out once you start talking anything above 18 gigabits per second. And that's been some extensive studies done by the aerospace and space guys who obviously they're keen to keep reliability and they're keen to keep what they understand, but have obviously started to realize there is some real limitations coming in there. So I think that's ample about theory for now. I think we'd like to run through a worked example or some real industry that you can really associate with. So customers' challenge is they've got a new digital processing unit for their satellite intercoms. And this new system is required to transfer 1 terabyte a second around the space payloads. So obviously, if you go down the copper route, remembering we said that this is, copper can't actually do better than 18. This is a theoretical exercise just to prove a point. You end up with 36 transmit channels and 36 receive channels to enable 1 terabits per second. Now, if you think what we said earlier, each of those needs a match pair for transmit and receive if you go copper. So you're instantly up at 72 pieces of fibre. That comes in a cable harness, so a bank of 12 channels is going to come in at around 40 millimeters wide, 5 millimeters in depth, and so weighing in at something like 40 grams per meter for the copper. The usual, again, because of copper, the connector systems and all the interfaces all require RF and EMC shielding to ensure that there's no effect of crosstalk and problems with the system, and also EMC emission from the system. So these connectors are usually very bespoke. They come in at about 60 millimeters wide by 20 millimeters by 6 millimeters, just to hold 12 channels. Now, also these are very, as I said, they're very bespoke, so usually have to be designed from start or are not usually available off the shelf. So that also then adds another increase in your cost to your program there. And that isn't really good. You don't want to be doing that. The other issue that you do have with copper in space is obviously there's a power consumption due to copper, and obviously the boost you need for the signal loss. And also there's an efficiency in there. Both of these are also affected by heat dissipation, heat that's generated during transmission that needs to be dissipated. And obviously once you're in space, it's not easy to dissipate the heat. So there's several reasons there why you can use copper, and an example of the size and the weight it would take. If we then move to optics to replace for this exactly the same challenge, as you can see by the images on the TV, on the monitors you're looking at, we're still at 12 channels. So a 12 channel system, you need 36, and as we've said, each ribbon fiber holds 12 channels, and ribbon's only 3 millimeters long by 0.3 of a millimeter wide, and it comes in at less than 4 grams per meter. That then, coupled with the fact you can use a industry standard connector, a multi-fiber connector, which you can see at the bottom left of the screen, which is called an MPO. It's plastic, so it's nice and light. You can actually get 36 channels into one connector, and you can actually have 36 channels running within the 3 millimeter jacket behind it. So essentially, you've got one connector that covers all 36 channels in a footprint of 12 mils by 20 mils by 6 mils. And as we said, because these products are off the shelf and they're industry standard, they're not expensive. You're probably looking at something in the region of 20, 25 pounds for the connector. So again, you're looking at weight save, you're looking at cost saving, and you're massive space and volume save by the fact that that one small connector replaces all of the large copper ones.
So Chris, we have a question from the audience.
Okay.
What is the cost difference between the MPO and the copper equivalent?
So the MPO will come in at around about 20 to 25 pounds. That's fully terminated on the fiber. For the electrical one with all the shielding and everything, you are looking at that being well in excess of 100 to 120 pounds for the connector. And then you have the termination time on top. The MPO will come in a fully terminated price at around 20 to 25 pounds.
Makes sense. Thank you.
No problem. So obviously now we've had fiber in the world for a long time. Most people only know it as telecos. So telecoms and, you know, telephones, mobile phones, internet and the such like. Actually, it's been adopted for many years in military aerospace. So for the last 20 years, there has been a fiber optic system in a military aircraft. So that's given us the opportunity to grow a heritage and proven reliability in a harsh environment application. So this is why we know that we can do this. We know the reliability is there. We know the strength is there because we now have a good 20 years of data behind us for a harsh environment in a military applications. This is the other thing that then strengthens the fact that there's a low risk now to move over to optics, whereas in the past, with a limited history, people were concerned about the reliability, especially for harsh environment. So this has carried on and grown. Both Generation 4 and Generation 5 fighter jets have mission and safety critical systems. And I'll show you some images shortly, and I can show you how much it's used in the systems. Commercial aircraft, two of the largest industry leaders have deployed fiber optic cables in their aircraft. And we're talking again, safety critical and mission critical. They're integrated into the taxi aid cameras, head-up displays, flight control system and cockpit systems that the pilots use to ensure safe flight and landing of planes. There's also an increase in optical transceivers in space applications, mainly driven through the fact that we need the high-speed gigabit data comms in there. But also the other advantage is you do not have to use any RF screening. You've got massive mass and weight reduction. And that's very desirable for space. For example, for every kilogram you can save in the launch, from the launch vehicle, you save a kilo of launch fuel. And last time I looked this up, the fuel costs £36,000 per kilo. So every time you can take a kilo out of the payload, you take £36,000 out of the program costs. Also, in addition, the fact that because the copper systems do suffer from RF interference, you then have to put in grounding loops and lots of shielding. Obviously, with optics, that's not required. So, first image is actually the optical data bus that we have in the Gen 4 fighter jets. The attack and the avionics are the two main data buses that are supported by optics within the Gen 4 fighter jet. API are very proud to be the key supplier of the optical transceivers that are in the Gen 4. We designed this system back in the late 1990s, and the system went operational since 2000. So we're in excess of 200 aircraft in flight, and there's 50 of our optical transceivers in every Gen 4 fighter jet. So when we say we've gained the history and we've gained reliability, it's not off one or two. As illustrating here, we've got 50 units in every plane, 200 planes in flight. If we were going to see reliability issues, that would be showing up during this period. And I've been involved with the program since beginning in the 90s. Not always at API. I have some background in another optics company that supply passive systems into the Gen 4. So I've been involved in the program since the beginning, and we have had no issues with reliability for the optical transceivers and the optical passive systems in this flight since then. So again, it's got good grounding and good sign of showing the key mission critical and safety critical components within military aircraft that rely on optics currently to keep them in flight. The next image, obviously to show that this is enough faith in that we've carried on. So now the Gen 5 fighter jets have increased their optical data bus. And from the image you can see on the screen now, you have some very significant areas within aircraft systems, electrical control, weaponry control, countermeasures, electronic warfare, that all the signals are received and sent to the processing units, and then all the relative what we should do about it is sent out of the processing units back through an optical system as well. So again, this is carried on showing high reliability. Gen 4 runs at 20 megabits per second data rate, which I guess when we look at today's standards is not a huge data rate speed. Generation 5 runs at 2.5 gigabits per second. But I know that they're now intending to look at increasing that because they want to start increasing the capability, improve threat detection, weaponry systems, weapon launch, and the reaction times within the fighter jet to keep it on point and keep it developing as the project goes forward. So optics is widely used in the current defense of the world, in two of the best military aircraft that are out there now. So there's a good heritage there, and again, proof that people have taken this forward. For example, as well, the Gen 4 uses an old style multi-mode fiber, which is specific and only used in Gen 4, whereas the Gen 5 has actually gone to the standard multi-mode system, and they run on the standard OM3 and OM4 cable. So they've already thought about actually putting inside a future-proofing so they can use more systems from more suppliers instead of being very limited due to their selection of fiber. That's enough about military now. We can move over to the fact that there's space applications. As Erica mentioned at the beginning of this webinar, that this is one of a series of 3. And the second one coming up will be keeping your lines of communication open, even in space. So I'll touch briefly on space here. In the next one, we'll go into far more depth of where optics is far more advanced in space and what we've done for the years of space. What you can see in this image here is a very clear demonstration as you've got signals coming into the satellite and you've got signals going out the satellite. That then telling the payload what they need. Because of the speed that's required now up in there, and that's at least 25-35% future proof there, so more information on when it's needed. That has to go up. It's going to be up there for 10 or 15 years, so it already has to have some future proofing in it and some increased capability sat there waiting. So again, where optics becomes very viable there is using it as the high-speed data link from all of the incoming information that's gone through the signal processor to be then sent to all of the control systems, so the data process, communications and control of the satellite. There's also then a lot of information being processed within the satellite that then needs to be then accumulated in space. And what we have in the graphic in front of us now is the conceptuals and a block diagram of internal payload. So the system on the left is a conceptual block diagram that comes out of a European space concept, which is where you have an RF domain with the information coming into the satellite. That would obviously then turn into an optical domain. Once received, it'll be transferred through the all of the systems within the payload, and then would then be finally converted optically from a analog to a digital signal to be put into the signal processors via the high speeds serial links, which again optical. The data processor would then produce, run through that, and then send the information back out via the optical HSSLs, right back through till it then gets converted back to an RF domain and sent back down to Earth with the messages. So that's taking optics and starting to integrate that within this payload communication system within space in the satellite. There is also the fact you could go and fully optics except for the digital domain. So again, on the right-hand side, the system's jumped away from any RF. So there's no RF signal coming up to the satellite. It's using optical power, high-powered laser signals that would come into the optical domain, be then taken through right up to the point that it's then sent to the digital signal processor into a digital domain there, and then vice versa all the way out till it's then sent back down to Earth. So these systems, step one is getting confidence and getting flight information and showing the robustness of optics within a space environment. And then the second step obviously is going fully optical, which is currently under design, development and test within one satellite system. So the guys have already started to put this into space and trust the fact that they're going to get information back and it will have a 15 to 20 year life. This is in a geo satellite application, not in a constellation. So the main things I think that sum up what we've discussed so far, we've gone through so far in this presentation, is the advantages of the optics versus copper. There's the increase in data, and when we say increase, we're looking at 10 times the data to go down a single core of fibre compared to a twin copper wire. Reduction in weight, as we said earlier, The copper is 40 grams per meter, and optical fiber is in the region of 4 grams per meter. So you're taking a significant 90% weight reduction just in the fiber. The electronics are again, similar, because you don't need repeaters and you don't need the bulk of the electronic system there. You also get about a 60% weight saving in the actual product. There's a significant weight saving carrying on with the actual size of the particular transceiver, and that's approximately a 77% saving as you go there as well. Obviously, optical fiber is completely EMC insensitive. It's just light being transmitted down a piece of glass. It's not affected. It's not, so you don't need to put any EMC shielding in there. You don't have to worry about crosstalk and noise from other componentry. You don't need to shield, so therefore you start to save a significant amount again in what you can put in size and volume going into the into your design, but also the fact that you can route it past electrically noisy environments and still have a good signal integrity. Again, because it is only light that is being transmitted, it's intrinsically safe, it's non-conductive, it doesn't create any, it cannot give any electrical discharge. Therefore, you can route it through some of the stranger environments. I've worked on a couple of projects where we've actually routed the fiber through the fuel tanks because it was the most effective route to run the cabling. So, you can run it through some of the strangest environments and explosive environments, and it's always going to be safe. Again, it's intrinsically secure. There's no EMCs being emitted, so you can monitor it or copy it. You can't just tap into a fiber cable. You break the fiber, it doesn't transmit. So again, you can't actually hack it. So it becomes intrinsically safe within the environment you're using it. Your distance is increased, and I think we've showed very clear that we're talking, 3 to 4 times minimum the distances that you're going to get the signal to go down. Therefore, how much more you're saving in the, the more fiber in optical fiber in there, the longer the distance, it's still not a massive weight increase. And of course, it is suitable for harsh environment. We've got ample reliability data. The fact that the VCSELs, the pins, and the optical fiber itself, by the way they're manufactured, the materials there, they're actually quite ideal for a harsh environment when packaged correctly. There's a question from the audience, quite a good question. How do we handle ITAR issues? So the product range that API do, we have designed and we manufacture completely within Europe, and the componentry that we put inside the system is actually all sourced within Europe. So there's no sign of any American design inside of it, which would then lead us to ITAR. Also, fact that this product is dual use and classed as dual use, so we will not see issues with ITAR. Hope that answers the question. So moving on to the point, I guess, where we should be, is the fact that this is the roadmap for our product, for API's products. The product is trademarked and trade named as OPTO-FIRE. So we have a roadmap, as you can see. We have a 10 gigabit quad transceiver that we launched last year. We have a 16 gigabit update system, which we'll be launching before the end of this year. We have 28 gigabits in development currently, which will be launched very early 2021. And that will come in a 4-channel transceiver or 12-channel transmit and a separate 12-channel RX. Again, that is being driven along voice of customer, that some applications would rather have the transmitter and the receiver separate. to where they want to place it on the boards. We then have started a feasibility study into 56 gigabits per channel, because we're seeing roadmaps from other people that are saying that within the next 5 years, they will actually require 56 gigabits per channel, purely again in space application, because obviously they're looking at putting the fastest transmitters in there. The device is packaged again for minimum weight and footprint, and we actually manufacture and qualify in full accordance to the military PRF qualification level for military and space. We have radiation testing has been performed on our 10 gig and preliminary work on our 28 gig for a total dose of 100 kilorads and a 60 MeV for the heavy ion beams that then will give it, will pass space radiation testing. So I have a question that I'm just trying to read.
Oh, I answered it for him, Chris. We'll take that one offline.
Okay, sorry. So that's the API roadmap for the harsh environment. So next sheet is the product portfolio that we have there and the part numbers. So 16001 is one of our early systems that we did in alliance with a customer for highly customized system. So this actually has 2 multi-mode transmitters in there and a single mode receive. It is a quasi-hermetic product. It has a pluggable optical interface. So that would enable for doing a BGA reflow before you attach the fibre. We do have operating temperatures of -50 to +100. So we're well within the, well meeting the military temperature standards and exceed most of the other optics systems on the market. Our systems are designed to run from 20 megabits to 10 gigabits in one unit. So they will run across the full data range. Whereas other people, you have them as, you can buy them in chunks of data rates, whereas our systems go right across the, from 20 meg to 10 gigs in the 16001 and 16003. Highly stable over the temperature range, extremely low power consumption. We're looking at 100 milliwatts per transmit and receive. They're completely protocol agnostic. They're, for want of a better term, a dumb transceiver. You can put anything in, you will get the information back out. And also radiation tolerant. 16003 is the fully hermetic version, quad transceiver. So you have 4 channels at a maximum of 10 gigabits per channel transmit and 4 channels that receive to a maximum of 10 gigabits. Again, completely protocol agnostic, stable across the power range of very low power consumption. And the third model you can see, this, the 16006, 7, and 8 is essentially our next release, which is the 28 gigabits. It's a fully hermetic package. We've been through the fact it's a quad, or you can have it as a transmit or a receive only. This system is custom and configurable, so there's a I2C handshake capability, so as any customer can switch channels on, off, and commit it how it would prefer to run it. We have an internal CDR and equalizer, which allows for any noise and issues that the PCB or the layout may have, and this system will clean that up without you having to put any extra circuitry in. Same temperature range, and on this one, we actually work between 1.25 gigabits to 28 gigabits. The CDR is set to work between 26 and 28 gigabits. Anything below that, you really don't need the the clock data recovery system to be used in the system. And on this unit, we're looking at 330 milliwatts per transmit and receive as a power consumption for that product.
So a couple questions from the audience for you, Chris.
Okay.
What qualifications or reliability testing has OPTO-FIRE gone through?
So OPTO-FIRE has gone through full mill PRF 3885, which is Class K, which is full space qualification under US mill, which is active shock, vibration, temperature extremes, tempo cycling, steady state, and quite a significant rest of tests, which has successfully qualified. And if people are interested in that full information, again, as we go to the end of the presentation, that is information that you can request and we can actually circulate to you, showing it's actually passed full military space grade qualification. And as for the radiation testing, that is to the ESA and NASA required radiation tests for space.
Fantastic. Here's another question. Normally, I know signals has to be carried by RF, but in the case of a full optic system, what is the carrier? Is it optic?
Yes, it's just pure light. So it's just so an electrical signal comes into our transceiver, that then is converted into essentially a digital knots and one light on, light off signal, and then it's pumped off, it goes down the fiber till it gets to the receive side of the other end, where that pulses of light are converted back into an electrical signal. So the carrier is purely just light straight down, which is formed into a digital signal. So if you have an RF in feed, you just need to have an analog to digital converter, which we can easily put inside the package and create that as one system. And there is a very specific RF over fiber application, which is used for some radar systems. So you can actually send analog signals via optics as well.
Excellent. And then finally, what sort of packaging does the OPTO-FIRE come in?
So the OPTO-FIRE comes in a HTCC ceramic package with a variety of electrical interconnects. You can have LGA, QFN, and BGA electrical interconnects with the standard ribbon fiber external. The 10 gigabit or the 16003 has a footprint of 25 by 25 by less than 12 high, and the 28 gigabit is 35 by 35 by less than 12 millimeters high.
Fantastic. And that's it, right? That's the end of your presentation. Is that correct?
That is the end of the presentation. As we've said, a big thank you to everybody for listening, and a very, very big thank you for you sticking with us during our technical difficulties.
So sorry about
as you can
that.
see there, if you have any other questions, there's a communications email address which you can submit those to. We have a resource page which has our success stories, some application successes, a video of myself explaining the 10 gig and working in a demo system, and obviously the data sheets that support our product range. But of course, if you've got any questions that you don't think that would cover, or you're interested in asking for any of that information, please use the communications address that's up on the screen right now.
Yes.
And thank you for listening.
Right. Thank you so much, guys. Thank you for bearing with us during your technical difficulties. All of the resources that Chris just mentioned will be emailed to everybody within the hour or so. And in addition, we'll also provide an edited version of this video so that we have no technical difficulties in that via email as well. Thank you guys so much and have a fantastic day.
Thank you.